Hey guys, today I want to talk about the awesome fact that our eyes are actually mini gyroscopes, or more specifically, our own built-in attitude indicators, just like on an airplane. Our eyes work in conjunction with the horizon, which is rendered by each person's eyes depending on his or her height and altitude. The horizon rendered by our eyes acts just like the horizon reference arm of a plane's attitude indicator, also known as the artificial horizon. Now, this also demonstrates that our eyes are built for a flat plane only. The functionality of our eyes and the fact that they always render the horizon at our eye level is what allows us to see using perspective, to distinguish up from down, a gradient that is sloping downward or sloping upward, near from far, and truly proves that we do not live on a ball. Now, when you turn your head sideways, the orientation of the object you're looking at does not change. This doesn't happen when you record a video sideways with a camera. In fact, that's very annoying. So why do your eyes do that? Well, it's because your eyeballs are mini gyroscopes. They do not turn with your head. They work just like a plane's gyroscope, but better. You can check this out in the mirror. Stare at a distinctive point in your eye or the iris, and then turn your head slowly, and you'll see that iris or your eyeball, it doesn't turn. Its orientation remains intact. So this is, I find this to be very cool. And the next essential feature of our gyroscopic eyeball is what it renders for us, the horizon. The horizon just doesn't exist out there. Our eyes render it for us. And it's the same feature as the artificial horizon line on the attitude indicator instrument of an airplane. So again, what is a horizon? A horizon is the line at which the Earth's surface and the sky appear to meet, to converge. And it's the convergence point of things below and things above into the vanishing point, or the point at which receding parallel lines viewed in perspective appear to converge. The point at which something that has been growing smaller as it gets further away, it disappears altogether. This is due to the limits of our eyesight. It's a creation of our eyes. If we could see forever, we wouldn't have the horizon line. But then again, without the horizon line, we would not be able to distinguish between items that are above us or below us, or taller than us or shorter than us in a distance. You've all seen the telephone poles in a distance. They will always, if it's taller than you where you're standing, they'll be above that horizon line, your eye level line in a drawing or anything. And just a linguistic note, this is very interesting. The origin of the word horizon, which we never think about, but if you think about it, it means horizontal or level. And the concept of level or horizontal is very important in this discussion. For instance, in Arabic, horizon is wafq al-mar al-aqli. I might have butchered that, but it has literally, word for word, the meaning of that is level man mental. You know, it's almost like our internal mental leveling instrument. It's pretty cool. In Hebrew, the word for horizon also means level. I can't pronounce it, but there it is. And again, you just realize that the ancients devised the word horizon because it is level, flat. In any language, horizon is going to mean horizontal or level. The horizon that our eyes render is our level. We have a built-in level. I find that fascinating. So to move on, the horizon, it gives us our relativity. Just like the airplane's attitude indicator, it contains the horizon reference arm. Our gyroscopic eye works using the horizon that it renders for us to act as our attitude indicator. And again, the horizon for us is the level marker, or artificial horizon on a plane's attitude indicator. Our eyes also create the horizon further out if we ascend in elevation, but necessarily still at eye level. If we go up in a lighthouse, our eyes will be able to see further, maybe 10 miles, 20 miles further, and they'll render that horizon at a greater distance, yet it's always going to be at our eye level. It's level. Our eyes create our horizon, which will be different for people depending on their height. If you're 4 foot tall, your horizon in your eye is going to be a different distance than someone who is 7 foot tall. But in all cases, the horizon is at each person's eye level, without fail, always. It's how we see using perspective. We need it. Like I said, our eyesight is based on perspective. So how do our eyes create perspective? Well, using our eyes as attitude indicators, our eyes render the stabilizing horizon line, and this allows us to determine whether something is above or below us, taller than us, or shorter than us. This is how we determine if a staircase is going down or if it's going up. It seems obvious and redundant, I know, but it is essential that we establish these facts when we ponder how ridiculous it is to claim that an ever-descending landscape would ever rise to our eye level. Just picture yourself standing on top of the ball Earth. It's impossible, for our eyes to function that way. We would not be able to distinguish between a flat, level plane and one that is descending away from us, because we just wouldn't be able to distinguish. That's not how our eyes work. We work based on the concept of level, horizon. Now, depth perception, that's another part of perspective. Objects in a distance will be smaller in size. It's with the amazing design of our eyesight. If I'm 6 foot tall and standing on a flat plane looking toward the horizon, any other individual who's 6 foot tall will always be at my eye level. If he's right in front of me, he's at my eye level. 10 feet away, he's at my eye level. 50 feet, a mile, 2 miles away, he's going to be at my eye level. That horizon level in a perspective drawing, that's that straight line across the page. No matter how close or how far away he is, if he's my height, he's going to be on, his eyeballs are going to be on that line. And now, say a man who's 4 foot tall, well, he's going to be slightly below that line. No matter how close or how far away he is, he's going to be below that line. And a 9 foot giant, well, he's going to always be above that line. If he's right next to me, he's going to be way above that line. If he's way off in the distance, his eyes are going to be above that line. This is the beauty of how our eyes work. And this is also impossible on a ball Earth. We're designed to live on a flat plane. So this is also how we're able to determine if we're walking toward a hill or a slope. You don't want to fall down a hill. Our eyes are designed so we don't fall down too many hills or too many staircases. Descending grades will never rise to our eye level unless they make it to a flat plane, and then the flat plane extends off into the distance. And then that horizon will rise to your eye level because you're based on a flat plane. This is how perspective works. In these photos, our eyes can distinguish between the downward gradients and the level sections. And like I said, the only reason the horizon rises to our eye level is because, we are on top of a level plane. Whether you're on, a hill or a valley, everything is built on the same level plane. So it will rise to your eye level. If it was on a ball, it would be impossible. No matter where you are or what elevation you're at on a ball Earth, the underlying base structure is a ball or a spheroid or a pear, which would necessarily descend away from you in all directions. Therefore, the horizon could never come to your eye level. If it did, it would be a crazy, confusing world like M.C. Escher drawings. You would not be able to properly distinguish between downward gradients, level sections, or upward gradients. Thank goodness our eyes allow us to distinguish between gradients and perceive depths. Otherwise, our lives would be one giant slam session, just like in skateboarding. And I know what that pain feels like. So, perspective. It's awesome. It allows us to perceive distances. Objects get smaller as they move further away from us. And elevation. The horizon line being the leveling line. Anything below is lower than us. Anything above is above your eye level. This is the leveling feature of our eyeballs. On a ball Earth, the horizon would never be at eye level, because in reality, it's always sloping downward. Why would your eye render it up at eye level? Just think of it, eye level, level. A ball Earth is always descending away. It would be deceptive. It's just not going to work. We'd be so confused. We would think we live, like I said, we'd be living in an M.C. Escher world. It'd be beyond belief. So I'm sorry. Our eyes just do not work on a ball Earth. And another thing I ponder as well, in true zero gravity, if such a thing even existed, how in the world would our eyes work? What would be the orientation to keep the eyeball, the iris, always coming back to the same orientation or remaining in a given orientation? And we can't replicate this because in zero-G planes, for instance, you're actually just falling. The orientation of the eyeball is the same as on the ground. The buoyancy and pressure, or if you want to call it gravity, well, I'll let you call it gravity for now, but whatever. It's still keeping the horizontal orientation of your eyeball in check, even on a zero-G plane and you're flipping around. But in magical deep space land, what would give your eyeball orientation? It's kind of sickening to think about that, but you'd be twirling around in circles. What would orient your eyeball? I don't know. It's pink unicorn land, but maybe somebody else can speak to that. But again, we all, I think, pretty much understand you can't trust NASA, so I don't think it's ever even, I don't think it exists. I don't think zero-G exists. So your eyeball wouldn't even function in zero-G, and without buoyancy and pressure, or if you want to call it gravity, but I don't think there even is such a thing as no gravity. Your eye wouldn't function. You would have no way to orient yourself. Your eyeball would spin in all different directions, perhaps, or you would turn and you would look like the camera. When you take a video and you turn that camera, it's so annoying, the picture just spins around. Well, in zero-G, maybe your eyeball would just lock into the socket, and as you turned, everything would just always constantly spin. It would be sickening. And the ISS, they'd all just be puking the whole time. And we know they don't clean it. We never see them cleaning it. So anyways, I know I got off on a tangent there, but I hope you find this as interesting as I do. Maybe it's old news to some of you, but I just kind of stumbled upon this. I just thought about it. I think it's amazing. But let me know if you have any comments. I'm sure that other people out there can maybe even go further with this and get more technical, make some other videos about it and how ridiculous the ball Earth is when you truly think logically about how our eyes work. So, thank you very much for watching, and have a great day.